Hi everyone, this is a demonstration of the WiSeDB project. This was joint work between myself, Ryan Marcus, Sophia Semenova, and Olga Papa Emanuel. Um, as System administrators move their applications from traditional data warehouses and on-premise IT centers into the cloud. They're faced with a number of different complications. The first is the increasing complexity of workloads. As the data science base gets bigger and as people have different applications and more products, they have much more complex workloads, which a much more wide range of queries that they need to process. The second complexity is a massive increase in the number of options within the cloud computing space. For example, the number of virtual machine types, different pricing options, and even different cloud providers. And finally is a variety of service level agreements, or SLAs. In other words, the performance that application developers need to meet. These three things make a very big decision space that give the system administrators a lot to think about. They create a lot of complexity in terms of how the various components interact. And most importantly, they make navigating the budget versus performance trade-off space very, very difficult. So in order to cope with these things, we propose using machine learning-based solutions to kind of replace what's happening now, which is that system administrators are just using kind of gut instincts or various very simple heuristics. So our goal is to optimize and try to decrease the amount of money that companies need to pay to infrastructure as a service clouds, as well as decreasing the amount of money in SLA violations that those companies would have to pay out to their clients. And we want to be able to do this for kind of arbitrary workloads, complex workloads, and for a variety of customized SLAs. So for example, for a maximum latency SLA, an average latency SLA, or a percentile-based SLA. This user interface sort of guides you through the process that a system administrator might do. So for example, we can select a couple queries here to compose part of our workload. We can then choose an SLA type. So I'll just choose a maximum SLA of 10 seconds. And the first system we'll look at today is a reinforcement learning system. So in this reinforcement learning system, queries are going to arrive one at a time as opposed to batch scheduling. And also this reinforcement learning system doesn't actually get to know what we just selected above. So even though here we picked that we had these three different query types with these three certain latencies, the reinforcement learning system won't actually know that. So it'll have no idea what the query arrival rate is. It'll have no idea what the different query types are. It'll have no idea what their latencies are. All of these things are unknown. And it's basically going to learn a strategy that's capable of doing this. So down here in these bottom two boxes, we have a visual representation of the strategy that the algorithm is performing. And this is happening live on the Amazon cloud. So currently, the algorithm is selecting a strategy that involves taking every query that comes in and spreading them out over a whole bunch of different virtual machines. Now it's slowly coalescing them onto a single one. So what you can see on the chart to the left is a comparison between our reinforcement learning strategy, rlearn, and the clairvoyant algorithm. The clairvoyant algorithm is basically what's the best greedy local decision that you could make if you knew the future, if you knew when queries were coming, if you knew how long each query could take. So our goal is to match up with that line because that basically represents making the best possible decision at each given time. And you can see that as time slowly goes on, these strategies will slowly converge. And so on the right, we have a large number of queries being processed on a set of virtual machines, and the algorithm is fully determining how many virtual machines to provision, what the size of the cluster should be, where each one of those queries should go, and what order that they should be processed in. So eventually, as you can see, the graphs slowly converge, and we'll see over time that they do eventually totally line up. So this system works by using a tiered system of multi-armed bandits. If you take a look at our paper, you can see some detailed diagrams that explain it. But essentially, there's a line of virtual machines, and each virtual machine has three different options when a query arrives. So when a query arrives, it's given to the first virtual machine, and that first virtual machine decides whether or not it's going to accept the query and add it to its own processing queue, whether or not it's going to pass the query to the virtual machine to its right, or whether or not it's going to send the query downwards. And downwards means sending it to a virtual machine of a different type. Either a faster or slower machine. So if the first virtual machine chooses to accept, it's processed on that first virtual machine's queue. And if the first virtual machine chooses to pass, a new virtual machine is provisioned to its right, and that query is assigned to that machine. So how are these decisions made? Each time a query arrives, each virtual machine pulls from its set of experiences and makes a decision based on that. each time a query finishes, we gain a little bit of experience. So for example, if we look at this particular virtual machine, we can see its current set of experiences. So every time a query arrives, we record the current CPU usage of the virtual machine, the current RAM usage of the virtual machine, the queue size, the number of queries waiting while when that query arrived, the number of tables used, the number of table scans that the optimizer predicts the query will have to do, the number of joins that the optimizer uses to execute the query, and the predicted number of cache reads that are inside of that query plan. Once the query is actually executed, we're able to know the actual cost that it took, how much money we had to pay in SLA penalties plus to the cloud provider, and the action that we took. So next time when a query arrives, we can build a decision model that maps these particular features, which we can read off the virtual machine, and a particular action to a cost. Then we select the action that minimizes that cost. This technique is called Thompson sampling, and it has some nice theoretical properties in that it guarantees a balance between exploration, which is what you see on the left side of this graph when the algorithm is trying a bunch of crazy things and trying to figure out what's going on, and exploitation, which is what you can see happening here, which is taking knowledge that we have from the past and exploiting it in order to get better and better schedules. So if we kept this running, it would eventually converge almost exactly to that orange line, which is a pretty good result. And the fact that we do this without using any latency prediction models is very important, because those latency prediction models, first of all, in the state of the art, only tend to be about 20% accurate, and they get much, much worse in cloud environments when you have to deal with things like noisy neighbors or different peaks in demand during the day because of time of day and when people get off work. So that's the reinforcement learning approach. We also have a supervised learning approach, which looks a little differently. So first of all, in the supervised learning approach, the algorithm does get to know the query templates and their latencies ahead of time. So you do tell it, okay, I have a type Q1 that takes 2 seconds, and I have a type Q5 that takes 8 seconds. So in this case, we'll go for an SLA of 9 seconds, and again, we'll stick with a max SLA. And now we'll choose supervised learning. So when I hit save here, what you'll see below is we just have to wait a little bit while our algorithm generates a decision model in order to do batch scheduling. So now with supervised learning, the queries are no longer coming in one at a time. We're now getting a batch of queries at once. And we're going to create a strategy that's capable of dealing with batches of queries. So we'll just give it a second. Right. So one of the biggest advantages of this approach is that we can allow system administrators to easily explore performance versus cost trade-offs. So over here on the left, we have the original SLA that we gave, which had a deadline of 9 seconds, and we know that the cost for running 5 queries of each type will be about 10 seconds. And here on the right, we can see how that strategy exactly played out. So we had Q5, which took 8 seconds, and we had Q1 that took 2 seconds. And our deadline is 8 seconds. So we're able to put only one instance of Q5 on a particular virtual machine before we run into a violation, but we can put 4 instances of Q1 onto a single virtual machine without having a violation. And then because of the numbers, we have to have a lone Q1 using its own virtual machine down here. But we can use this decision model to explore this cost-performance trade-off space. And here we generate a couple of other SLAs that exemplify kind of critical turning points or very important points in that cost versus performance trade-off space. So for example, right now we have a 9-second latency, but if we go up to a 19-second latency, we can save about 3 cents. So you can add 10 seconds to your deadline, and you can decrease your costs by 30%. So if we use this particular SLA, then we can see that there's a new strategy here, and we can see that 2 Q5s are capable of fit, followed by 1 Q1, because we have 8 plus 8, which is 16 plus 2, which is 18, and then we have a slight 1 second padding for noise. So these models are completely agnostic to the number of queries in the workload, so you can very easily change the numbers of various queries. You can increase and decrease them, and the schedule will adapt and modify itself to that. So we'll go back to the original SLA here just so we can see it. So down here we can see a comparison between WiSeDB, the strategy that we come up with, and first fit decreasing, which is a common heuristic that is used to solve the bin packing problem, which is highly related to what we're doing here. So here you can see we're predicting first fit decreasing to take about 6.3 cents, and we're expecting WiSeDB to take 6 cents. So a very small win, but again, it was a machine learning generated strategy. A human being didn't have to pick the particular heuristic. We can also run this on a real cloud right now. This runs on the Linode cloud. And we can see what these results actually look like in terms of the payments we would have to make to that provider and the payments from SLA violations. So you can see here that we actually ended up being much more even. WiSeDB took 6.66 cents, and this put 6.6 cents. So in this case, the heuristic actually did slightly better than us, but that's not generally the case. So how do these decision models end up being made? So they're represented as decision trees, which are reasonably basic and easy to understand. Basically, what this strategy says is if we have an unassigned instance of Q5, and if we do, then we follow down this yes branch here, then we check to see if an instance of Q5 will fit on the last provisioned virtual machine. If it will, then we place that instance of Q5. If it won't, then we'll generate and provision a new virtual machine. If we don't have another unassigned instance of Q5, then we check to see if a Q1 will fit. If it will, we'll place that instance of Q1, and if it doesn't, then we'll create a new virtual machine. So this strategy is very simple, and it basically just explains how to pack a batch of queries onto a number of virtual machines. So for example, we can also go down to this SLA of 15 seconds. We can get a slightly different thing. Now the difference in the predictions is much larger. We a whole 0.8 cents, so almost an entire penny, although of course if we had hundreds of queries that would be much larger. We can run it on the cloud again and see what those actual results are. There's lots of noise from cloud environments. There's variance because of noisy neighbors. There's variance based on network times. Sometimes disks are a little slow, but you can see here that first fit decreasing took a cost of about 4.96 seconds, and we beat that by a slight amount at 4.89. And you can look at our papers to see more examples of the decision algorithms that we come up with. Generally, this gap gets bigger as the workloads become more complex and involve more query types. So if you're interested in these particular projects, check out the WiSeDB projects from Brandeis University. If you type us into Google or click on the descriptions and the links in the descriptions of this video, you can read the actual papers. Thanks.